see my screen? Can everybody see my screen? Yes?
Yes.
Okay.
Yes.
Very good. Okay, so in this homework, you'll work on the famous MFCC, the Mel-frequency Cepstral Coefficients, 梅尔岛频谱的系数. Okay, this is the most commonly used feature or feature vector for speech recognition. So I'm going to introduce that to you today. And also this first term, onomatopoeia, I'll explain in a moment. It refers to like sometimes we use some certain words to describe sounds, and there are examples in every language. So that's homework number 4. So this is number 4. The objective of this homework is to invite you to ponder upon what kind of proximity makes two signals sound similar. Okay, by proximity I mean distance. So how do you define, how does a machine automatically calculate or evaluate whether or not, or to what extent two sounds sound similar? So here's the example. Here you'll be hearing a sheep, a call from a sheep, a real sheep. Let me play it. Can you hear it? Yes?
Yes.
Okay. And here is me faking the sheep. Okay, I'm not sure if I do a good job, but that's my attempt. So we all do that as a kid or even as adults. So this leads me to think about, since this semester we are going to focus on vocalization, human voice. So I wonder, when we try to imitate the sound of certain things, then how do we evaluate who is doing a better job? Okay, let's say if you fake the sheep, I fake the sheep, who is making it more similar to the original sheep? That's the kind of question we are asking in this homework. So we'll take this chance to look at a prototype of earliest speech recognizer. And I'm serious about this. So earliest speech recognizer, for kind of for example, to recognize digits, 1, 2, 3, 4, 5, discrete digits, right? 10 possibilities, and you need to classify. So those kind of speech recognizer early times uses, most of them uses dynamic time warping for time domain alignment, and we'll show that in a moment. And the feature they are using to compare the distance between the query and to classify classification is a Cepstral distance. Note that Cepstral is really spectral, but spelled, the first 4 letters are spelled backward, spec, right? S-P-E-C versus C-E-P-S, Cepstral. So that's why in Chinese translation, we call it 岛频谱, the kind of opposite spectrum. That's the Chinese translation, 岛频谱, that's the reason. So so this is outline, right? So in this homework, you'll be looking at what exactly is Cepstral coefficients, and how and why may that represent sound similarity. I don't mean to play this again. Yeah, all right, so the activities are, yeah, first in the folder, okay, let me, yeah, in this ASAS folder, let me get back to the e-learning. So in the folder in the home material, yeah, in here, you'll find the 4th homework, okay? And I have uploaded a few files you can listen to. And so the first activity which I invite you all to try to do is to imitate those sounds. And so let me play the sounds. The first one is that sheep. And the second one is a bird call. Is it loud enough? Is the volume okay?
Yeah,
Yes.
we can.
Yeah, okay. Right. And the third one is a drum. And there are a few more sound effect clips, such as this one and this one. Okay, I believe some are harder and some are easier. Okay, so but please try to, as much as you feel comfortable to do it, try to imitate the sound by mouth. So when I say by mouth, one question maybe, can I whistle? Does whistle count? I think yes, yeah. Especially when if you find it hard to mimic the sound of this bird call, anything that you produce by mouth is okay. That's kind of the rule, all right? So the question then is, how do we evaluate whose imitation is the closest to the original? How do we evaluate? Of course, we can evaluate the performance subjectively by creating a chart rating from 1 to 5. That's one possibility. But now the question for this homework really is in 2 weeks, I want you to survey and to research how do we do that automatically? How can the computer do the same? How can the computer evaluate how close two sounds are, how similar they are? You see, I'm trying to just go to the next page. All right, so here are some related topics. So as I mentioned, onomatopoeia is the process of creating a word that phonetically imitates, resembles, or suggests the sound, the sound that it describes. So for example, I'm pretty sure that every language we have a word for dog's voice, right? In Chinese, can anybody give an illustration? How do we call 狗怎么叫? Anybody? Easy one in Chinese. 叫 Wang, right? Right. So any objection? Have you heard any other way of describing how a dog bark? How dogs bark? How about our? Yes. 谁在讲? Please, yeah, again. Oh. That's a different kind, right? Right. So we probably most agree that dogs do. 他们是汪汪汪汪汪汪. That's a Chinese word for dogs. But how about since we have some international students, I want you to share. Yeah. For example, how do Americans or English speakers, how do you describe the sound of dog?
We usually use woof, woof, woof.
Wolf, right, with an F in the end. But, yeah, so that's different from Wang. And there is no right or wrong, but I found that it to be interesting. Okay, and
we also have a bow wow wow.
Bow wow wow. All right. Yeah. So I wonder, yeah, each society, each culture may have a different way of describing sound, yeah, different words. Okay. And another example is rooster call, 公鸡叫. Can our Taiwanese students demonstrate how we usually call 公鸡叫, rooster call? Or in Taiwanese? What is that? That's pretty good. Yeah, go. All right, go. How about our American friends?
Cock-a-doodle-doo.
Right, can you spell that in text? Yeah, well, I want our students, I know it, but I want everybody to see how different they are in your language, in English.
I think that's how you spell it. I'm not very sure.
Okay, let me take a look. Dialogue. Cock-a-doodle. Yeah, something like that. Thank you, Alex. Cock-a-doodle. Right?
Cock-a-doodle.
Doodle.
Jonathan is correct. That's the right way to spell it.
All right. But one way or the other is very different from the Chinese way. We say gu gu gu, right? Basically, gu gu gu. Yes. Okay, so some other examples, for example, that I want to. So this leads me to recall a song that that went viral a few years ago. It's called "What Does the Fox Say?" Let's watch it together. So this song is about how I just really love this song. It's hilarious to me. 我觉得超好笑. I don't know. Ding, 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 ding. Best song ever. Right. So yeah, so that's I think there's a deep question in here. So how can we have words for different animal calls, and they're all different depending on which culture, which language you're using. So where is my PowerPoint? Let me switch back to my PowerPoint. Oh, I may have to, wait, where's my PowerPoint? Where's my PowerPoint? Oh, right here, okay? All right, so what does the fox say? And so some other examples, including raining. So the sound of raining. So we've, it's pretty nice that we kind of discussed the sound of filtered noise. Sometimes they sound raining, but how about the word? There are some words, how about in Chinese? How do we describe raining? 雨下的怎么样？下很大的话 If it's raining heavily, how do we describe it? 雨下很大怎么讲 Anybody?
哗啦哗啦。
哗啦哗啦，哗啦哗啦. That's raining. Okay, 哗啦哗啦. And how about table tennis? How do we call it? Table tennis is what?
Ping pong.
Ping pong, right? Ping pong is onomatopoeia, and I think it's a good example of onomatopoeia because the sound of the ping pong balls bouncing on the table is like ping pong. But then the question, why don't we call it ling long or sing song or something else? So I want you to take this out. I want to invite you to think about these issues, right? So how about raining in English? Raining. Do we have a word?
Pitter patter is one that I've heard, but I'm struggling to think of a specific word. Maybe Jonathan knows something better than that.
Jonathan? So how do you spell, is it pitter patter? Pitter patter, right? Yeah, I've never heard that. Yeah, I've never heard that. Thank you for sharing.
Regional differences.
Regional differences? So that's, how about in around East Coast?
I'm from the West Coast, so I can't answer that one.
Yeah, I know you're from California. But how about Jonathan?
Okay. No, that works in the East Coast too.
Okay, cool. Yeah. Okay, so that's about the onomatopoeia. At least it was a new word to me. I learned the word not long ago. And so another related topic would be beatboxing. So I think this homework also could lead us to think about, is there any, like, since we are trying to imitate the sound, right? So is there any limit of like a set of all possible sounds that human mouth can make? And for us, it's limited, but for professional beatboxers, oh, they can do like amazing things. So here's a video I'd like to share to you. That's one example. We see this guy reaches, this video reaches 55 million views, right? And he's not even American. Did you notice? At first, he was saying French to somebody, to his friend, c'est bon. So he's not even American. I assume he's not. So that's pretty amazing, isn't it? I really admire those people who can do this. Okay, yeah, it's amazing to me. So I want to share with you that, let's get back to the PowerPoint. If you're interested, actually, there is an academic paper written by Professor Shrikant and Narayanan of USC, University of Southern California. And he is the advisor of Professor Jeremy Lee, okay? And he's an excellent scientist, engineer, and educator. And they do diverse research topics in all different fronts of speech processing. And one paper that I encountered a few years ago at this conference, Interspeech, is what they're doing here is to compare beatboxing articulation. Articulation means to pronounce, basically, to produce a sound. So they compare like expert and novices using MRI. All right, so if you're interested, really check it out. This is amazing what they're doing. And they found out that when professional beatboxers produce the sound, the way they put their lips and tongue and chin, the way they articulate is amazing. Really can be beyond our imagination. Okay, so there's a technical paper that you can refer to. All right, so Anyway, with that, let me just continue to give you a short tutorial on the main topic, the Mel-frequency Cepstral Coefficients, or MFCC. Okay, so, oh, by the way, please interrupt me anytime. You can press the space to interrupt me anytime. Press the space to unmute yourself, all right? So I welcome that. So here, the first slide I'd like to share with you, Mel is a frequency scale, a nonlinear mapping from Hertz, okay? So Mel is from low to high. So for example, in this curve shows the formula, M, Mel is equal to this much times log 10 of 1 plus f divided by 700 Hertz. So that's the curve. So from 0 to 10,000 Hertz, this maps to roughly to 0 to 3,000 Mel. But why do we make this nonlinear definition? It has something to do with the way our ear processes the sound. So let's say the sound enters your ear through the ear canal through the middle ear and pushing through the 3 bones to push the fluid inside the cochlea. So if we look inside, the cochlea is like the shape of a snail, the cochlea. If we unwind the cochlea, straighten the cochlea, you'll find that in between there are 2 compartments, 2 fluid-filled compartments, and they have different names. But in between the compartment, there is a basilar membrane, something called the basilar membrane, which can allow the wave to propagate from the entrance part to the top of cochlea. And so it turns out that the mapping here is what we call log linear, which means that when the wave proceeds by 1 unit distance within the cochlea, the frequency drops by a fixed ratio. And that's why, so, is that clear? So log linear. Okay, unit distance in the cochlea, fixed ratio, roughly speaking. So the mapping really is nonlinear, but more closer to Mel-frequency mapping. So that's why we have that curve in the previous slide. Okay, so a bit more detail. So in around 1943, this Hungarian scientist by the name of von Beckerschi. Okay, so by that time, he was able to do some experiments to actually measure human cochlear responses to pure tones. And here he found out he basically had some cadaver, some human specimen. And he opens up the cochlea to measure the mechanical response at different places. Here we have 6 different curves and each representing 1 place. 6 different places along the cochlea. And he measures the frequency response of these different places. And you find that the frequency response, except for this one on the very far left, the other 5, 1, 2, 3, 4, 5, the shape looks similar, right? This is a frequency response. The shape, I hope you agree that the shape, the triangular shape, 这个三角形, the 5 of them look similar if we take the logarithm of frequency. Here is a cycle per second, Hertz. The scale here is log. It's after taking logarithm. So this is the kind of first clear evidence, experimental evidence that human hearing is log linear. Human frequency perception is log linear. Any question? We have a question here. What exactly is the y-axis? You mean right here?
Yeah.
Yeah.
What are they measuring precisely?
Yeah. So I might be wrong, but I think he used some certain kind of optical measurements. So maybe by shining, I'm not sure, is laser available right there? That's a good question. I have to check. Thank you for, I'm not sure exactly what this is. Yeah. Probably not the rate of hair cell because these are dead cochlea.
So he's just looking at like the mechanical ways within
exactly
itself.
Right. Yeah. Dead people. Yeah. And don't ask me. I wonder how come he gets so many dead people to do experiments on. In 1943, of Hungary, the Austro-Hungarian kingdom, you know, the Axis enemy. Right. So that's one of the earliest experiments like this, and he actually won the Nobel Prize in 1962. He was awarded a Nobel Prize in medicine and physiology. So important work. Okay, so now here, these are the way that we try to mimic the result obtained by von Beckersheim, these triangles. Now we just simplify them a little bit, and we call them Mel-scale triangular filters. Okay, so here you see like a series of 20 triangles in Hertz. And you note that the width of these triangles are from narrow to broad, from narrower to broader. And turns out that they all correspond to the same width in Mel scale. Okay, remember Mel is a kind of frequency compression, right? So at higher frequency, 1 Mel corresponds to a wider range in Hertz. So that's the idea, from narrower to wider. And you can use this formula to figure out exactly where are the boundaries. Okay, any question here? Mel scale triangular filters. And in next few slides, I'm going to explain how we use the triangular filters to convert our signal into a Mel scale representation. So here is how it goes. So here, for example, say we have a spectrum like that, a magnitude spectrum. And one of the filter is right here. So it's pretty easy. We have a total of 20 of them in this example. And what we do is that for that exact filter, for each of the filter, we would, what we do is to perform weighted sum of magnitude, 加权的这个总和 weighted by the triangle. Or another way to put it is you perform inner product between the triangle vector and your magnetic spectrum. And there are 20 of them. So that leads us to 20 different results. So far, so good? Is it clear? Is it clear? You sum the total magnitude within the frequency range by putting a weight, the triangular weight. So which is 1 in the middle and 0 when approaching the border. Okay, so we have 20. If we have 20 of them, we convert the magnitude spectrum into a vector of size 20, an array of size 20. Okay, and next is to take logarithm of this. Okay, the standard procedure way of defining MFCC is first take so this vector is called the Mel energies. The Mel energies from band number 1 to band number 20. Okay, Mel energy, and you take the log. So after taking log, we see that the kind of tiny parts become more exaggerated. So we can see more detail nearer to 0. So that's one step. And after taking the log, we perform DCT, the discrete cosine transform, I'll show you in a moment. So discrete cosine transform is sort of a version of inverse Fourier transform, okay? It's similar to Fourier transform, and the result is, so the input has 20 dimensions, and output also has 20 dimensions, okay, in principle. So let me mention that in this chart, so before DCT, we talk about band number, okay, band number 1 to band number 20. But after this DCT, we call the unit domain there the frequency domain. Again, this is a kind of a, how do I say that? Frequency, but with first few letters put in we arrange the first 5 letters, frequency, frequency. And sometimes in Chinese, we call it the inverse frequency, the 导频率, frequency, to emphasize that this is frequency, but after inverse transform, you kind of convert it back to a sort of a time domain. But here I'm refraining from calling it the time domain because it really is not the time domain. But sometimes we call it the frequency. Okay, frequency number 1, frequency number 20. So far, so good? So here next, I'd like to show you the definition of DCT. How are we doing in time? DCT, okay. DCT is given by this formula, okay? So here you have the frequency M. frequency m from 0 to L minus 1, L being 20 in our previous example. So m equals to 0, 1, 2 to 19, 0到19. Okay, that's the frequency. M is the frequency. And then what we do is similar to Fourier transform. Basically, there's a matrix, you perform the inner product of x, your log of Mel energies. This is the x vector. You perform inner product of x with 20 different basis vectors, which are plotted right on the right. So here is m equals to 1, m equals to 2. That's a basis function, okay? M equals to 3, 3, 4, 5 to 19. So I'd like to pause a little bit to see if you have any question right here. This is important because this sometimes gets confusing. So I want you to, I really want this to be clear at this time. Any question regarding this formula?
I don't have a question on the formula, but I have a question on something else.
Yes, is it
So
related
if
to?
no one has any questions, I'll go ahead, but others can ask questions first.
You can go first.
Why did they decide to take the DCT? It seems kind of like an arbitrary choice. Like, what's the reasoning behind calculating the energy and then taking the transform of the energy?
Right.
Would the answer change if you used more subdivisions of your Mel, like more triangles?
Oh yeah, it's definitely that would be different. It depends on the result. Actual result depends on your choice of L. Definitely.
And then what's the reasoning for like the discrete cosine transform? Why not like discrete sine transform or a regular Fourier transform or anything else?
I totally agree with you. Yeah, this is quite arbitrary. Yeah. I do have an answer, but I want to hear other opinions. Does anybody have your opinion, or have you heard about the reason why they have chosen DCT? Anybody? Here's one response. I don't know. Good. No. Okay, so my answer, I try to answer this. Okay, this is a good question. I think it is indeed arbitrary. Okay, but it has some people say that DCT tends to decorrelate the band number, the band energies. Okay, by mapping it to the frequency domain, there is a kind of effect of decorrelation. The way I tend to think about it is that because DCT, you're right, Alex, you're right, DCT is just a version of Fourier transform. So the frequency actually is if you look at this figure, okay, if we just forget about how they're derived from the band energy, it's just a curve, right? This is a curve and this is a pattern. Or you can even say, even cooler, you can say this is an image, a one-dimensional image. And so, which has different pixels, 20 pixels, okay? So naturally, what we can do is to do the inverse for the Fourier transform of this picture to the spatial frequency domain. So the result for different n really now has a kind of a visible meaning. N means a spatial frequency. So low frequency means slower spatial variation, whereas high M, low M versus high M means more rapid spatial variation. If you take this, you regard this as a picture, as a one-dimensional image. I'm not sure that this is my way of looking at it. I hope it helps.
So basically, you're finding a way to look at the spatial frequencies of that image so that you can compare distances between different images?
Yeah, and even one further step is that traditionally, people do that all the time. Traditionally, we take only the first 13. I don't know why, the choice of 13, but that's been done like for since ever. People choose the low frequency part and ignore the high frequency part. I'm not sure exactly why that's the case, but yeah. But you're right. This is mapping, spatial frequency. I think frequency means spatial frequency. If you take this as regard this as an image, okay? Should I continue?
It makes sense to me.
Okay, we have a few more comments coming in. So is DCT another kind of magnitude? DCT another kind of magnitude? Yes, in the frequency domain. And kind of a tiny detail here is that DCT, we also, if I'm correct, if I'm right, we choose a normalization factor C so that DCT becomes a unitary transform, which means that DCT preserves vector nodes. And when we map it to the frequency domain, it's still 20 dimensions, but then we kind of project it to the lower 13 dimensions. That's kind of a standard way of creating the final FCC feature vector. So here is a kind of a summary of the entire flow, right? So from any input signal, you can first perform windowing, chopping them into frames, and the frame across different adjacent frames, you can choose to overlap them or not. And let me also mention that Matlab has a built-in function for you. It's a part of the signal processing toolbox, an MCC function, right? So after windowing, we go to the FFT domain, and say if the window size is 1024, for example, after FFT in the frequency domain, it's still 1024. Then we take the magnitude part. Take the magnitude part, ignoring your phase, and the length becomes half of that. So overall, you'll find that we gradually reduce the dimension from 1024 to 13. So that's kind of the motivation behind this entire flow, underlying this entire flow. So after taking the magnitude, now we have only 512 numbers. And then, as I mentioned, we perform inner product with 20 to 40 triangles. To take after here, what we get is the log, what? Log of it's the Mel energy. Okay, we call the result after here to be the Mel energy for band 1 to band 20, if you will, band 40. Okay, and let me also mention that in Matlab, there is a property that goes with MCC function that you can use, which specifies how many filters there are in this step. Okay, band edges, please check the help. All right, so after taking the band energy, then we take log. Remember that we take log, right? To kind of enlarge the tiny part. So after taking log, then we apply the final step DCT. And it's, since it is a unitary transform, it's mapped, it preserves the dimensionality. So if it was 20 for the input, 20 in the output, 40 in the input, 40 in the output. But then, as I mentioned, we traditionally, people take the first 13 coefficients, and these are called the MFCC, the Mel-frequency Cepstral Coefficients. We often take the first 13 of them. Take from from m equals to 1 to m equals to 13, the first 13 of it. Okay? Any question here? 这边有没有问题? Allow me to also mention, okay, so here is a dialogue. Is a 13-point cutoff related to human hearing sensitivity? Good question. I'm not so sure. Yeah, but yeah. Specification frequency decreases after 20. Exactly. Yeah, that's true. That is true. All right. So certainly, I think MFCC is a very nicely engineered way of representing speech signal. So all these are, each intermediate step has a reason. I believe, for example, taking log has a reason. Taking log has a reason. It has something to do with our perception of loudness. Okay, that is like you increase the loudness, the intensity of sound by, let's say, 10%. Every 10% of increment sounds equally large a jump to a higher volume. Okay, so in that case, we can say that the human volume perception is also log linear. So that every single step may have a reason. So, but I encourage you to think about why I discussed. But let me also mention one further remark. Here, when I said the Mel coefficient, I say m equals to 1 from 1 to 13, right? But how about m equals to 0? So the zeroth MCC is actually the log and called the log energy. The log energy, and if you just plug in m equals to 0 right here, cosine of 0 is always 1, right? So effectively, we are summing all the log energies, and the result is our 0th vector. So summing all over 20 or 40 bands, and the result is the 0th MFCC. And sometimes you find that in some implementations, the 0th MFCC is often ignored. And with that, I'd like to switch to my Matlab demo of MFCC calculation and dynamic time warping. Okay, here is my Matlab. And so here is the code which I also uploaded to the folder. And in this homework, you will be asked to load 2 files. For example, here in this example, I'm going to load the file of that sheep and my fake. Okay, that sheep and my try. That's me faking the sheep. And so in this code, first, MFCC will be for the 2 signals are calculated right here. So I encourage you to play with different settings of MFCC. This is sort of the baseline. And for example, I didn't bother to try to change the number of bands. And I checked the default is actually not 20, but 40, 42. Okay, so you can change that or change the window length, change whether or not you want to overlap, and there's different things you can try. And then the result is stored in, I believe, in the coefficients. Okay, so if we look at the side, yeah. So the coefficient will be, let me just type whose. The size of that matrix, the coefficient, as you can see, the length of the original signal might be something close to 96 or more than 100,000. But then we transform that, represent the signal into 13, into 187, or a number of, this is a number of frame. Okay, the number of frame for the first signal, the number of frames for the second signal, and it becomes a 2-dimensional representation, and each frame is associated with a vector of length 13. 好吗？每一个 frame 都有13维度的一个 representation. So it is stored right here after calculating MCC. And then after that, we try to calculate how similar they are. So here, let me run the code first. Okay, so as you can see, here is the original waveforms. My imitation and the original sheep, or the opposite, the other way around. I forgot. But anyway, one is the sheep, one is myself. Probably this is no, I'm wrong here. No, forget about this. This is wrong. Okay. Anyway, this is a sheep, and this is me, and they are not even aligned. But the cool thing about dynamic time warping is that it allows us to, it automatically aligns which frame is similar to which frame between the imitation, my imitation, and the actual target. So let me show you the results. So in this this code, the second part right here, we thank TA Jimmy for providing the code for dynamic time warping. So basically what it does is to, based upon the distance, how similar each frame is to, what each one frame in the target is to the, how similar it is to the each one frame in the faking one. So it calculates, it finds out the path, which is shown here. So here you're looking at a black and white image, a grayscale image. And here, the x-axis and y-axis are frame indices for the imitation signal and the target signal, and they are not equally long, right? The lengths are not equal, but that's all right. What this does is to first, dynamic time warping first calculates the similarity between each frame in this signal and each frame in that signal, creates a matrix. Is that clear? So, so here, this picture has so many pixels that every single pixel represents how similar this frame is to in the limitation, how similar it is with respect to any given frame in the target. And here, brighter, the kind darker means shorter distance, and brighter means longer distance, more alike. Okay, more alike. How do I say that? More not similar. Okay, more not similar. And so the dark part means similar. So here you see that my attempt, at least the dynamic time warping finds this blue path. And this blue path has the rule which allows it to go only 3 directions. It can only go to the right, or downward, or to the bottom right. Only 45 degrees. Okay, so only 3 at every given pixel, it can only go 3 different directions. It can not go backward. Okay, it cannot go backward. And then dynamic time warping finds you the path which has the smallest total distance. That's what it does. It finds the path of smallest total distance. And we thank Jim for implementing this code. It's pretty standard. So as you can see that, at least for this example, the DTW algorithm successfully, at least it finds that it should try to go through this dark part, because these regions are all very similar. And I feel good about this. It means that my try of meh is really similar to the original shape call, right? This dark, that's what is shown in this dark region. And the algorithm successfully finds the path to go through mainly through like 45 degrees, more or less, through this region between my imitation and the target.
Is it finding a global optimum, or is it like finding a local optimum path?
I believe it's global. Yeah, I believe it's global. Subject to the rule that the path can only go to the right, to the bottom, or 45 degrees. Yeah. But I might be wrong. I might be wrong. Yeah. Anybody have any comments on this? Anyway, so the code is given to you. So let us know if you think something's wrong, incorrect in it.